We just want to go over just a couple applications of partial derivatives. Let's return to a Cobb-Douglas function and just really kind of pick one of these things apart. Suppose a Cobb-Douglas production function for a company is given by z of xy equals 150 x to the 2/3 times y to the 1/3. So remember, these kind of production functions are always of this form. The two exponents add to 1, and then X is usually investment, capital investment, in however many thousands of dollars, and Y is labor force. In this case, it's in work hours, or it could be just total people employed or whatever. So there are always some constant times X and Y to powers that add to 1. So let's pick one of these things apart. So when you see the word marginal at this point in this course, you just know you're taking a derivative. So I don't even know if I defined marginal productivity, but you know what it means. Take the derivative of the productivity function. So the only thing we need to know here is which variable it's with respect to, because it's a function of two variables. So we're just saying, okay, fine, this is just zx. Y to the 1/3 is just a constant in this case, so it comes along for the ride. The 2/3 hops out front, times 150 times x. The exponent goes down to negative 1/3. I mean, that's a piece of cake compared to the kind of stuff we've been doing in this class. Let's clean it up a little bit. So let's just write 100 x to the negative 1/3 times y to the 1/3. So if we hold the labor force constant, which is what we're doing when we find a marginal productivity with respect to investment, we're holding the labor force constant. So let's just hold it constant at 729, like a specific number, and let's just look at the marginal productivity graph and just interpret it and just make sure it makes sense as far as what we're talking about. So that's what the function becomes. 729 to the 1/3 is 9. So that looks like that is 900 over the cube root of x. And then we're not considering x to be negative because x is investment, so it's only positive. So that's what that looks like. We can kind of think of what we know about asymptotes. As x goes to infinity, this marginal productivity is going to go to 0. So for one thing, the zx is always positive. So the rate is always positive. So the more money we pump into this company, the more productivity we're going to have, period. There's no cap to how much productivity we can have. But this function is decreasing pretty fast. So what does that mean? It means at some point, it just means the rate at which productivity is increasing is going down. So the more money we throw at it, yeah, we'll get more productivity, but it'll be less effective as we throw more and more money into it as x increases. So there's that as a statement of fact. So all I really need you to be able to do is know what, marginal productivity and margin and with respect to the two things mean, and maybe graph them and for sure interpret them. Okay, piece of cake. This is just zy, so you know the drill. The 1/3 comes out front. X to the 2/3 is still a constant, so it just comes with. The exponent goes down to negative 2/3. There is a negative in front of that 2/3. It's hard to see, but it's there. So it's 50x to the 2/3 times y to the negative 2/3. Right, because 1/3 times 150. So now let's just hold x constant, like again we do when we're taking partial derivatives, and let's just call it a certain thing. So it's 27 grand, and we're just going to do the exact same thing with the marginal productivity with respect to labor force. So just plug that number in and simplify it. Turns into 45,000. I just rewrote that as the cube root of y squared. So, and there's the graph. It's red now. So it looks exactly the same. So everything, right, because everything we just said about marginal productivity with respect to capital is true for labor as well. So if we keep throwing more and more people and more labor hours at it, yeah, this rate is always positive, so productivity will keep going up, but it'll go up less and less. So that's it. Let's talk about demand functions. So we have two related products, and in this scenario we're going to talk about they are competing. So they're Nike and Adidas, or Pepsi and Coke, or whatever. So we have demand functions, and both of the demand functions are based on the price for both items. And that's, if they weren't related, it wouldn't be. So if you have two of the same types of thing and the price for one goes up, but the price for the other one doesn't, generally the demand for the other one is going to go up, right? Because more people are going to buy it. So that's why both these demand functions are functions of both prices. So my function here is demand, and my two variables are the prices for product 1 and product 2, P1 and P2. So we have Q1 and Q2. So that we just put the word marginal in front of something, and that means it's a derivative. So now, the only difference is we have two different derivatives. So the demand for Q1 is going to change if its price goes up. I'm sorry, for product 1, and the demand for product 1 is also going to change if the other one's price goes up or goes down, right? If the other price goes down, then the demand for our product probably goes down because more people are going to be buying the other one. So that should kind of ring a bell and make you think about like positive and negative derivatives. Okay, so that's pretty simple, right? If two products are truly competitive and you just fix one price, and the other price goes up, then the demand for the other one will go down. And this is what we mean in a mathematical sense when we say two products are competitive. If the change in P1 with respect to P2 is positive, and the change in P2, the demand for P2 or product 2 with respect to product 1's price is also positive, that's just what we're saying in this scenario, is that the products are competing. So increase in price of one will result in an increase in demand for the other one. So let's just do an example of two products like that. So there you go. Okay, so this isn't a hard example. The demand functions for two products are given by Q1 equals 900 minus 9P1 plus 2P2, and the demand for product 2 is 1200 plus 6P1 minus 10P2. So we're just going to do some math and find out if these two products are in fact competitive. They're obviously related because their demand involves the prices for both of them, right? So, this is like Toyotas versus Hondas or something. If Hondas got really expensive, you'd probably sell more Toyotas. So we're just going to kind of pick this apart and look at it. Right, first we want to see what it would look like for the demands to be perfectly equal. And this isn't calculus. This is just setting two things equal to each other and solving. I guess it's all calculus. So when you solve that equation, you're not going to get one single solitary value for P1 and P2. You're going to get like a linear relationship. So I skipped the algebra because it's easy. Basically solve that for P2. You could also solve it for P1 and just see what it looks like. It looks like that. P2 is 25 plus 1.25 P1. So if you think about that as a graph, that would be a linear relationship, right? It's like mx plus b. So any pair of prices that satisfy that, non-zero, non-negative, are going to result in the demand being perfectly equal. So you can just plug numbers in. If P1 is 40, then 25 plus 1.25 times 40 is 75. So if P1 is 40 bucks and P2 costs 75 bucks, they're both going to theoretically sell the same exact amount. Okay, so since there's two functions and they each have two variables, there's going to be four total marginal demand functions. And all I really want you to be able to do here is explain to me what they all mean, what all of the partial derivatives mean. Okay, dQ1 with respect to P1, quite simple. Everything else goes away except the negative 9. Now let's think about what that means. The change in demand with respect to its own price is negative. So that means if the price goes up, the demand goes down. It's that simple, which makes sense for almost every single product you can think of. The more gas costs, the more people are going to, ride their bikes. So as price goes up, demand goes down. So that's what you would expect for all but like a few weird commodities that you could think of. That's going to be the case. The partial derivative with respect to its own price should be negative. So that really, on the next test when I ask you interpret this, that's all I need you to say. Just something as simple as that. Okay, same deal here. So everything I just said is true. As Q2's price goes up, its demand goes down. Duh. So here's just the other two just at once, because as you can see, it's incredibly easy. So the change in the demand for product 1 with respect to the price of product 2 is 2, so it's positive, and vice versa as well. The change in demand of product 2 with respect to the price of the other product is also positive. It's bigger. So all you have to do is say, okay, that means that as P2, as the price of product 2 goes up, so does the demand for product 1, right? You raise the price of one, more people are going to want the other one, because in these scenarios, we're holding the other price fixed. So that's all that says. And then obviously the same goes for product 2. If the price of product 1 goes up, so is the demand for product 2. Therefore, these products are competitive.